The other ones won't, so you'll still need it. Out of a total of R residents in a nursing home, the number of residents who have been infected by the flu increases at a rate proportional to the product of the number of residents who have had the flu and the number of residents who have not had the flu. So, if S denotes the number of residents who have had the flu at time t, write a differential equation that could be used to model the situation where K is a positive constant. All right, so let's label our variables. So what does S stand for? Number of residents. I think I should be able to fit it here without extending the page. I'm going to just put with flu, or who have had the flu. Yes. And then T is our time. K, what is it? Constant. Is our constant of proportionality. We'll just write constant. And I see a capital R. What's it? Not radius. It's not the radius of the nursing home. Total residents. Okay, so the question says write a differential equation that could be used to model the situation where K is a positive constant. So what we're monitoring here is the number of residents who have had the flu, right? So our differential equation needs to be ds dt. That's going to be the rate at which the residents are getting the flu. Yes. All right, so that ds dt, if we go up here, it says the number of residents who have been infected by the flu increases at a rate proportional to the product of the number of residents who have had the flu and the number of residents who have not had the flu. So our number with the flu is increasing at a rate. That's our ds dt. And then it says a rate proportional. What's that tell us we need to put? The K. That's our constant of proportionality. And then it's proportional to the product, which means we've got two things we're going to be multiplying here. The number of residents who've had the flu and the number of residents who have not had the flu. So number who've had the flu, what is that? That's S. And then number who have not had the flu. R minus S. Yeah. So, because it's the product here. So this would be our differential equation. It is only asking you to write it. So that would be it. So whenever we are, this first part really tells you how to write the differential equation. This part sort of defines your variables and tells you what it's looking for, so it's asking for that differential equation. So whenever we see the number of residents who have been infected by the flu, that makes us think S, but then it says increases at a rate. So that's the rate that S is changing. And so rate that S is changing is going to be our ds dt. When we see that that rate is proportional, anytime we have something being proportional, we assume that's like direct proportionality, which means we've got K times the number there. A really good example of direct proportionality is whenever you get paid per hour. That's your K. If you get paid $15 per hour, that's the K, 15 times the number of hours you work. So K is like our rate that this is spreading here. or that constant rate there. So, and then it tells us here that we have the product of two things that's coming up. So the two things that we have the product of are number of residents who have had the flu, which is our S, and the number of residents who have not had the flu. And so the ones who have not had the flu, we would take, you have either had the flu or you have not. There's no in between. So you would just take the total residents and subtract that. Does that help? Okay. You will see, so looking forward, today we're going to finish this up. We got a couple more notes that we're going to do, and then we'll have an assignment that goes with this. We will have, this is our last section, though, that we are going to do for Unit 7. So we are going to tomorrow work on some progress checks. Thursday we'll review a little bit more, and Friday is going to be the test. That also means your FRQ is Friday. Yes.
I'm not going to be here this Friday. I'm sick. I got COVID. I'll be here.
Good.
I still have a couple of excuses, but I won't be here.
Okay.
Yeah,
All right.
that's that part.
Hmm?
That's that part.
Okay. It's just you, though. That's only you, right?
I'm going to have... This Friday.
You're getting the Deltacron.
Yeah, I'm going to
Yeah. We'll get yours made up next week. So,
Yeah, do it Thursday for her.
she wants to take it Thursday. If she wants to take it Thursday, she can, but
I feel like she should.
I'll let her do it next week if she would rather. It'll be okay. We'll get it. We'll get it made up.
For the whole weekend.
It will go in as a 0 for a little while, but as long as you make it a blue time. All right. So the test is going to be on Friday. You will see a problem like this. It'll be on multiple choice section. So there's no work to solve, but you'll have just options there.
So it's just reading comprehension. Oh, God.
Yeah. Okay. All right. Let's look at example 4. This also means the free response quiz that I gave you guys gave you guys yesterday. It will be Monday instead of Friday. So here we go. Okay. All right. Okay. All right, so a tank with a volume of 30 cubic feet is leaking. The rate of change of the volume with respect to time of the water leaking from a tank is proportional to the cube of the volume.
I don't like the word proportional.
Okay, so the first thing we have to do is we have to write the equation for the differential, or the differential equation for this relationship, and then it's going to ask us to solve some stuff about it. But we got to get that differential equation right before we can do anything else. So we have a tank with a volume of 30 cubic feet. V is going to be our volume. We're looking at dV dt. Just that equation. Yeah. Yep, it only asks for the equation. So, the rate of change of the volume, what is the rate of change of the volume? dV dt, with respect to time, is water's leaking from a tank, is proportional to the cube of the volume. Volume cubed.
Oh, go crazy, Tommy. Tommy can, in fact, lead. Literacy master over here.
All right, so this is your differential equation. Okay? Questions about it before we move on? That's all for part A.
Daniel. I don't get it. I'm lost.
So,
Why did the V3 up here?
Because
So-
it's just cubic volume.
because it is proportional to the cube of the volume. So that means the volume cubed and not just the volume itself.
Oh.
As a new one, shut the door for us. Yeah, it's just Sarah. Okay. Alright, so now let's figure out this. So at t equals 0 minutes, the tank is full. 30 minutes later, the tank has a volume of 25 cubic feet. Find how long it will take for the tank to have only 10 cubic feet of liquid left.
I'll reckon 30 minutes. Right at 30 feet a minute.
Okay. So
Those numbers.
before we can plug in any of those numbers, we need to solve the differential equation. So we're going to have dv dt equals k v cubed. We can't do anything with that dt in the denominator, so we're going to multiply by dt over here. And we need the v over here on this side. So we need to divide by that v cubed. So we'll have dv over v cubed equals k dt.
And one of those V's can cancel out.
It cannot, because dv is a separate variable, Thomas. Alright, so we cannot cancel those v's. dv is a separate variable. Think of it like a z or something. It's not. It's not. Those two are together and cannot be separated. It's not really v, right? So we need to integrate both sides. What are we going to get when we integrate that left-hand side? Oh, I was so hoping somebody would say natural log. All right, so if that was dv over v, it would be natural log. You would be exactly right. But that's v cubed. So we want to think of it like this: v to the negative 3 dv. Think of it with negative exponents.
She just enumerated that junk.
Okay. So it was in the denominator. We move it up to the top so that it's a negative exponent. Then we can just use the power rule for it. So that power rule, whenever we do that, Alfredo, what will we get when we integrate this? Daniel, let's quit heckling the class today, okay?
I'm innocent.
Uh-huh. Negative 1/2. Not v squared, negative 2. And then on the other side, Alfredo, what are we going to get? No. K is not our variable. Daniel, I'm going to take your bathroom passes before I do have them today. I need them too. So your variable is t. That's why that dt is important, because that is the variable that we're integrating. So k is just a constant. It's like having a 3 or something there. So it's kt. And then what do we need? Plus c.
So, could Daniel
So if you were integrating just 7dx, something like that. If you're integrating something like this, it's just a constant. It'd just be 7x. So k, we got to treat it like it's a 7. So it's just k and then whatever variable our dt is there. So like if we were integrating 5dp, that would be 5p.
It's because the eagle has a hook and it catches the mouth of the bee.
Yeah.
Okay. All right. Okay. So we have now solved the differential equation. So we wonder how long it will take for the tank to only have 10 cubic feet of liquid left. So we got a few options of what we can do here. We need C and we need K. We could try to solve that for V first. I think it's going to be easier to go ahead and plug in and find our C and our K. I think. These are usually FRQs when you see them, yeah. A lot of times these are 5 or 6 problems, or 5 or 6 points. So you get a point for separating, a point or sometimes 2 for your integrals here. This would probably just be 1 point for the integrals because they're not terribly complicated ones. Sometimes it's a point just for the plus C.
Like, would it just be like, would it ask you this and then it'd be worth 6 points, or would it ask you like 6?
It would just ask you this and it would be worth 6 points.
I think it needs to ask the question.
Yeah, it doesn't do that. But it would just ask this. So the main thing here is it's asking us about volume. All of this information is just about volume. Nothing says anything about a rate. So our differential equation is not going to do us any good because it would have to all relate to a rate of something. So we have to solve this so that it's just a V, so we don't have that rate, that dv dt there anymore. And then we can plug our information in. A point or 2, probably, yeah. Yeah, and you have to, usually they don't do this on FRQs. Usually, what's going to happen with this is usually, the part A might be a multiple choice question. Usually in a free response question, they're going to give you part A. Because if you get part A wrong, then you have no chance of getting that. So usually they don't give you, they might give you one that builds, but they try not to be missing such an important piece of information there. So probably if this was a real FRQ, they probably would have given you that somewhere in the problem. They might have asked you a tangent line problem or something before this, or slope field, and then they would ask this last part. So you wouldn't usually see these two together in an FRQ. So let's look at our information. At t equals 0 minutes, the tank is full. How many cubic feet is full? 30, right here. So at t equals 0, our volume is 30. So that's going to be negative. I'm going to do this. I'm going to do negative 1/2. And I'm going to do negative 1 over v squared, so 30 squared, like that. Because we could write this negative 1 over 2v squared equals kt plus c. It'll be a little easier to evaluate if we don't have those negative exponents. And then we'll have k times 0 plus c. So we're solving for that c. So whatever we get in here, which is going to be like negative 1 over 1800, is our c. So if we go back up here to our equation, that means we got negative 1 over 2v squared equals kt, or I'm going to put a minus, instead of plus, minus 1 over 1800. Then we've got another piece of information at t equals, what was that time? 30 minutes. The tank has a volume of 25 cubic feet, so at 30 minutes, oh, let me think for a second. Yeah, we'll do it this way. Volume is 25. You have pause there for a second. You have an option of using minutes, or you could use hours. So you just need to know which one you have used, so you know that your answer is in minutes or hours. When we integrated it, it became squared. So we'll have negative 1 over 2 times 25 squared equals k times 30 minus 1 over 1800. And we're going to rely on the calculator here. I don't think it would be quite this bad. Alright, so this is negative 1 over 1250. We'll be adding 1 over 1800 to that, because we'll be that is going to give us you don't have a rate. So the original equation, the DV, you don't have the K. Now, if you plug in 0 here, it's going to make that K go away. Right, because you'll have a 0 multiplied by your K. So you have to use that second piece of information to find this. Alright, so this is our K times 30. So we got to divide that by 30. Alright, so negative 11 over 135. This, I'm not sure. But, it would be impressive if I could do that without it. Alright, so, if you'd rather use a decimal, of course decimals are fine. Also, I was avoiding the decimal because I thought it would be a long, ugly decimal. Somebody let Ethan back in.
Is it 4 zeros?
1, 2, 3, 4, 5 zeros.
But on the top, right?
Oh, yes. Thank you. Thank you. Alright. Okay, so that's our K. And so now if we go back to that equation that we've been using right here, negative 1 over 2v squared equals negative 0.000008 t minus 1 over 1800. 5 zeros. Whew. Alright, we're almost there. We're wanting to know 10 cubic feet left. So we're wanting to know the time when our volume is 10. So we're almost there. Okay, so I will need, that's going to be negative 1 over 200. I'm going to need to add the 1 over 1800. And if this were on the exam on Calculator Active, you don't have to show the work for solving every step. So, you know, you could do this in the calculator, but you would need to show like where you plug things in. So we're going to do negative 1 over 200 plus 1 over 1800. So that gives me negative 1 over 225 equals negative 0.000008 t, and then we'll divide by that negative 0.00345. Alright, so we get our time is 555.55 repeating. What are our units for that? Minutes. Now you could have chosen, instead of using 30 as your time, you could have chosen to use 0.5 as your time. You'll get a much smaller number. I don't think the numbers are going to be much better whenever you're doing the problem. Maybe, but you get a much smaller number, but it would be in hours.
So if I don't put minutes, do I lose a point?
Possibly, yeah.
Okay,
Especially in this where it did not specifically ask for hours or minutes. You've got to tell them which one it is because you could use either one.
And if I get it wrong, but I do say minutes, do I get a point for that?
It just depends on whether or not there's a unit point on that problem. Sometimes there is, and sometimes there's not. Okay, questions? That is, no, you do usually need to do like a little bit. If it says indicate units of measure, that means, that almost always means there's going to be a unit point somewhere. Sometimes it's just on that specific part. Sometimes it might say indicate unit measures on 2 or 3 parts, and you have to have the units right on all of those parts to get credit. So, but if you can't come up with the answer, like you're stuck on it, do something to come up with the answer, and if you know the units, put the units, because you have a chance of getting the unit point even if you don't have the correct answer. Even if you did crazy stuff to get the answer. Yeah, so. Okay, this is a very, let's skip. Alright, this is a very important question. So, you have a Hot Pocket, and it's removed from the microwave. I forgot to go look that up and preview it to see if it's appropriate, because I can't remember. He's usually not that inappropriate. He's usually pretty clean, but the Jim Gaffigan, he's a comedian. He has an entire little bit on Hot Pockets. Go look it up. It's funny. But I did not preview it, so I better not show it right now, because I realize that you guys are all about grown, but still, I don't need to be in trouble for showing you something inappropriate. Maybe I will preview it and we may watch it later. So, probably, but
You watch someone get lynched. I'm pretty sure
probably. I'm sure you can. I just don't want to be in. I don't want to be endorsing things that are inappropriate. And we don't have time, so let's move on. All right. So a Hot Pocket is removed from the microwave and set on the table to cool. The rate of change of the Hot Pocket's temperature, T, with respect to time, little t, is proportional to the difference between the Hot Pocket's temperature in degrees Fahrenheit and the room temperature of 73 degrees. So A asks us to write a differential equation, and then we're going to do a really important calculation to figure out when the Hot Pocket is going to reach the optimal eating temperature of 150 degrees. We actually did this experiment one year. It's been like 3 years ago. We may do it after the AP exam here if we get time. We did pizza rolls instead of Hot Pockets so everybody could have pizza rolls. Yeah. Whenever we did our experiment, we did try to decide what the optimal eating temperature. We thought 150 was actually pretty good. Because if you think your body temperature is 98.6, so something's going to have to be hotter than 98.6 for you to feel like it's hot. 150 was pretty good, although Joe Gallion felt like the men could take a little bit hotter than that.
Oh boy.
Yeah. So Joe and Rhett were they the only? No, Justice was also in there.
Just.
But I think it was Justice. I think there was one more boy. But they were the only boys in the class. Maybe it was just Joe and Rhett then. We don't need to go down that rabbit hole. But anyway, Joe, I think Joe and Rhett were the only. No, it was Tanner Upchurch was the other boy. There were only 3 boys in there, so they would always get together to do their work. The 3 boys, and they would put their work on the board, and they never put their names. They just always wrote the men. So they felt the men could take a temperature of a little above 150, but perhaps the women would not be tough enough to take that. So you think about that what you will. So Daniel's on that side too. He
I would think that it would have smoke because you eat it and then you like blow out smoke like that, right?
and can't feel the inside of your mouth for the next week. Things start to peel. Yes. It's been a long time. Yes, it has been a long time since I had more boys than girls in calculus. I think that I don't know that I've ever had more boys than girls in calculus except for, I think that first year that I taught calculus, I think was 2015. I think I had more boys then, or maybe they were even. My boys were the strongest in that class. And I think it's been girl heavy every year since then until this year. So. All right, so, all right, we got to write the differential equation. The rate of change of the hot pocket's temperature. With respect, it is D, big T over D, little t, is proportional. That tells me to write K. To the difference tells me I'm going to subtract something between the hot pocket's temperature and the room temperature of 73 degrees. I think technically we could do 73 minus T, but we usually do T minus 73. Well, no, whenever you say difference, whichever one comes first has to go first. So, T minus 73. Okay. So, this is Newton's law of cooling. But it didn't tell you it was Newton's law of cooling, right? So, you may see a problem that is given like this where it doesn't mention Newton's law of cooling at all. But it is Newton's law of cooling. That is your ambient temperature, which in this case is 73. That's your room temperature. Okay? So, 20 seconds after being removed from the microwave, the temperature of the hot pocket is 205 degrees Fahrenheit. I use 20 seconds because unless you have a super good instant read thermometer, you're going to have to wait you're going to have to wait just a little bit for it to like reach its actual temperature there. So, just trying to be realistic here. 1 minute after being removed from the microwave, the temperature of the hot pocket has dropped to 187 degrees Fahrenheit. Estimate how long it will take for the hot pocket to reach the optimal eating temperature of 150 degrees Fahrenheit. So, if you want to eat your hot pocket as soon as possible, but you do not want to burn your mouth, you need to know what this time is. All right? This is see. But then you may miss out on the, or you can be like Daniel and just burn your mouth. So we have to find this information. So we need to solve the differential equation first. So dt over dt equals K times t minus 73. The dt, we're going to multiply on both sides. We have to get rid of the big T, so we're going to do divide by t minus 73. Good job, Chandler. Henry's working on rhyming words right now. He was doing a really good job rhyming words with itch the other day. Had to correct that one, which is not even good because he doesn't know what it is. So you like, I really don't even want to teach it to him, but like he just kept saying it over again. Mama, these words rhyme. Itching. So I'm hoping he doesn't actually remember the word, but sometimes when he like says things he's not supposed to, but I know he doesn't know what he's saying. He's just like repeating something that he heard. You know, like he loves to like walk in when you're watching TV and like catch one thing he's not supposed to say. Not that he's not sitting there watching. Well, sometimes he does watch things with Hunter that are like not like bad, but not great, but a little bit. So, but usually I just ignore it because he doesn't know what it means, so he's probably not going to say it again. But this time I have to press it.
Oh, I figured out it was a bad word early on, and then in kindergarten somebody said it, and I was like, "Did you just say shit?" And then Marcus on the other side of the room told on me, and I had to go talk to Miss Morrison.
I need you to go see Mr. Morrison. All right.
No, you should see me go talk to Mr. Morrison.
Yeah.
Yeah.
He would be angry with me for sending you, probably.
He'd laugh and say,
Yeah. All right, so. All right, so we're going to integrate both sides. And we're going to do e to the power on both sides. What's going to happen to our plus c here? It's going to become our multiplier here. And we need to add our 73.
Good job, Laura. Wow. She's not dumb anymore.
Alright. I'm hoping that we can be quiet and get through these so all of you guys can make a little higher on that test. No one was having their most impressive performance on that midterm. So some were better than others. Some were better than others.
I was closer to my average.
I was okay with my grade. That's the best I've ever had.
All right, so once we get this solved, this is to the point like what you would be doing, like Coach Wood was doing problems like this. So your calculus is done at this point. He may not do it every time. Yeah.
No, we started with it and then we stopped. Like
right.
Yeah, like we were doing all this more on the side. We wrote it down, and I had one problem. It was on one day.
Yeah. You were online, weren't you? No. Oh, I don't know. Perhaps he did not see much potential. I don't know. All right.
I saw logs.
Okay. All right. So, now. It tells us 20 seconds after being removed from the microwave. The temperature of the Hot Pocket is 205 degrees Fahrenheit. So here's the problem with that. If we plug in 20 for our T, then to have two variables. I have a c and a k. And I'm not going to be able to solve if I have a c and a k. I really want to plug in 0 for the t. Because if I plug in 0 for the t, then I can get the c, right? Because the k is going to go away. So, how are we going to deal with this? Because I don't have a time equals 0. Any ideas on what we could do? We need t to equal 0.
So why can't we just put 0? I missed that.
Very good. So let's do that. This 20 seconds, let's actually let it be our t equals 0. And capital T is going to be 205 at that point. But that means this 1 minute, we need it to be 40 seconds. So if we're going to let our 20 seconds be our 0 seconds, then we have to make that 1 minute actually 40 seconds there. We're basically just scaling it back here.
You're just like starting it from 20 seconds later. All right, Jack.
Starting what?
Did
we just like manipulate time though?
Yes. We went backwards in time 20 seconds. Or forwards, which way, I don't know. We just lost 20 seconds.
We did daylight savings.
Yeah. Okay, so we're going to have 205 equals C, E. Yes, Newton. Yeah, this is Newton too. Newton did a lot of stuff.
Newton did not do a lot of stuff.
I don't know if he really created it, but
No, he created gravity.
he did quantify it. Did describe it.
For that apple, we discovered.
I think creator of gravity might go to God. So we're going to get 132 for our C. Right, because our e to the 0 is just going to be 1, so it's going to go away. So now we've got t equals 132, e to the kt, plus 73. Then we have our second piece of information. We're going to let that t, even though it was 1 minute, we're going to go backwards 20 minutes and let that be 40, not minutes, seconds. And then the temperature there was 187. And so we're going to plug that information in. Let's use our solve on the calculator just to see if we can do it faster. It's not that hard of an equation to solve.
Times or minus 40?
Times.
I was thinking.
Alright, I'm going to use solve on the calculator just to see if I can do it any faster.
Can you do a solve and then like put a derivative inside of the solve?
I think, but sometimes you make your calculator mad and do something it can't handle.
Yeah, I put too many commas.
Yeah, Margaret broke her calculator today.
Margaret concussed it.
Yeah. Margaret did concuss her calculator, didn't she? Alright, so we've got this. Oh, let's hit green button before we hit enter. Alright, I used an X instead of a K, so we've got, I think that might be a little faster if you want to use that instead.
Where did that K come from? I mean, X.
I used the X in the calculator and then I wrote it down, but it should be a K. I think the calculator can solve it if you use a K. It's just harder to type in, so. All right, so there's our equation. We need to know when our Hot Pocket will be at the optimal eating temperature of 150 degrees. So we're going to plug in the 150. Yes, 665. Let's use our calculator again to solve this. So that's going to be 150 and to the, oh, I don't know if it'll let me do that. If I go up here and hit enter, it's going to, if you go up there and like hit enter, it's going to put that x equals, so make sure you take that out if you do that. And that needs to be, you could use a t, I'm going to use an x. And so I get 147.062 seconds. Now, something important. What did we do so that we could have a 0? We took 20 seconds away, right? So we need to add those 20 seconds back. So 167.062 seconds from the time it leaves the microwave.
So what's the significance of playing with time?
That's almost 3 minutes, yeah.
So by the time you solve this problem, it'll be ready.
It's probably going to be cold by the time you finish. By the time you do this problem.
It just took us like 9 minutes.
I made up this problem, I think, before we actually did the real experiment. So that may not be accurate.
It also depends how long you put it in.
It does.
So it's 2 minutes, awesome. 3 minutes.
It depends on what time.
This would be super specific to a particular particular time, because your room temperature would have to be 73. The Hot Pocket would have to come out at 205. So, like if you had a hotter microwaves can vary a lot too based on how strong they are. So, it would depend on a lot of factors. That's why your microwave instructions are going to tell you that you got, I think the microwave instructions usually tell you to let it cool for at least 2 minutes. Yeah. Yeah. And microwave and microwave instructions will also, give you a range on your time as well. So,
You know what I never
and they have lots of warnings telling you it may be hot to avoid lawsuits.
Is there like a section that just looks like a little pizza symbol, and then you press it, and then it gives like 5 minutes on the pizza, pizza like that. It doesn't make sense.
It's on like it does it on like a lower power so that your crust doesn't get all like hard. And
I always thought it was like 5 minutes.
yeah.
That's like 9, 10, 10.
Yeah, it's not like it won't on my microwave at least. If you hit the pizza button, it does heat it up a little bit better because it doesn't heat it up at as high of a heat. But then you have to wait for like 3 minutes for a slice of pizza when 45 seconds would have been fine. But the crust is not quite as like hard. You know how the crust will get hard. No, like if you were reheating a leftover piece of pizza, I think is what it's for. Yeah, that's also yes. Yeah, we added 20 back to it. We got 147 also, but we added 20 back to it because we made that 20 seconds out after it came out of the microwave. We made it 0. So, yes.
Why did we play with time again?
The reason that we played with time is because if we had tried to do the T equals 20 and capital T equals 205, then we would have had 205 equals CE to the K times 20 plus 73. And that equation has two variables in it. You've got the C and the K, which are two different types of constants. So if we fix it by putting a 0 right here, K times 0 is 0. Which, and e to the 0 is just 1. And so that you can solve much more easily. As long as you add it back at the end. Yes, it's differential equations, so it'll be all the things that we have learned on differential equations. But so some of it was before the midterm. We just did. I would have liked to get that test in before the midterm, but we just didn't have time. So, all right. I do want to do a couple more problems with the exponential stuff so that you can see these. We're probably not going to do all 4 of these. That should say exponential instead of exponential or whatever I wrote there.
Exponential.
Yeah. That's not you might need paper. All right. Okay. All right. So, we did one of these at the beginning of yesterday's notes. So, you've seen one of these before. I just want to do maybe 1 or 2 more so that you're a little more familiar with it. So, whenever we see the model for exponential growth and decay, it arises from this statement: the rate of change of a quantity is proportional to the size of that quantity. So it could be something like the rate of change of population is proportional to the size of the population, right? Or the rate of change of the number of bacteria, is the one we had before, is proportional to the amount of bacteria that you have. So, yes.
What is proportionality again?
Proportionality is telling you that you have that constant, that K, times whatever variable. So, rate of change of a quantity, let's pick a variable to use for quantity, Q. So, dQ dt, that's your rate of change of the quantity. When you see is proportional, that's your equals K, and the size of the quantity would be Q in this case. And so that, whatever that quantity is going to change a lot. It could be population, it could be bacteria, it could be the amount of money you have in an account, it could be all kinds of things. But if you see something where the differential equation looks like this, we solved it the other day, and you multiply both sides by dt. I told you guys yesterday, this is a little bit like the inverse of related rates. It's like they're giving you the differential equation, and you're going backwards from that. So if we divide by q, we're going to get dq over q equals k dt. You could, yeah. The upper and lower case really just depends on what they tell you in the problem.
Hang on.
The main reason I've used upper in some of the other ones we did is because they had a capital S there.
Tommy, you can't do it.
You do cancel those Q's. Don't cancel these Q's. Cancel those Q's right there. Yeah, don't cancel these.
I see.
And we would integrate both sides to get natural log of the absolute value of
Okay,
Q.
constant, though.
And then KT plus C. And then E to the power here, your quantity is going to equal CE to the KT.
Oh, that's the same thing.
Yeah, I know. Q is a terrible variable. I regretted it
Same thing as like
as soon as I wrote it down.
It's the sideways.
It's the same as the PE to the RT. So, if you see one of these, usually they're on multiple choice. They are usually not on free response whenever they have these problems. If you see one of these problems, and it says, like in this case, the rate at which the population of a town, so rate of the population of a town, is proportional to the size of the population. That is dP dt equals K times whatever the population is, right? So if you notice, you have this setup where you've got dP dt equals just K times that P. You can jump to P equals CE to the KT. So on the AP exam, I have not seen these show up on the free response, but if they did, it is okay to make that jump. Most of the time it's on multiple choice where it doesn't really matter whether or not you show your work anyway. So if we want to find the rate of change of the population, we know that in 2000, the population was 6,000. In 2010, the population was 6,522. So whenever we're doing the PE to the RT, maybe you shouldn't use P, but so this C right here, that's our initial value, right? So I'm going to let 2,000 actually equal 0 so I don't have huge numbers to deal with, which means I should make 2010 equal 10, right? And so my initial population is that 6,000. You could plug in the 0 and the 6,000 if you want, but you're just going to get that C equals 6,000 because that's your initial value. And for just straight exponential growth stuff, that's going to be the case every time. If it's Newton's law of cooling, if it's something else where you got to solve the differential equation, don't make that assumption. But it is okay to make it here. Basically anytime they don't give you a 0, anytime they don't give you a 0 for you to use, you want to make your lowest number 0 and then adjust the other one accordingly. So because we need that lowest number to be 0. If it is not, the only way you could do it is like a really complicated systems of equations that would be terrible to solve. I'm not sure if we even know how to solve it by hand, so we would want to do that. So we've got this information. We also know that when t equals 10, the population is 6,522. So 6,522 equals 6,000. We did this in pre-calc.
I remember it.
We did do this in pre-calc. We didn't do the first part where we have the differential equation, but divide by 6,000. Yep.
Yeah, this is more my slave.
They already quit when I give them factoring problems. I can't do that.
Yeah, me too.
Natural log both sides. Some of my kids in pre-cal, they're pretty smart. Oh, I'm sorry. I should have replaced T instead of K. That should all my T's right here should be K. Sorry. Yeah, let's change all those to K's there. Sorry about that. My time is 10, so I should have a K right here.
Oh, we just omitted the 0?
No, the 0 is the P equals 6,000.
So K is going to be our rate of change, but if we're wanting to give this as a percentage, it would be 0.8342%. Yeah, this one's the rate of change, which will be that K. Usually rate of change.
How could that population not be like DP
Um,
over DP? Why is it K? I thought K was.
yes, but that would be an equation that you would have. So this is your rate of change. It's not a constant rate of change. It's your exponential rate of change. So it's the percent that you're increasing by
So it's
each
like your
time.
rate at the time.
Yeah. So it's that it's your exponential rate of change, which is really your growth rate. Another phrase that might have been better there would be your growth rate. Okay, so the part B says if the population continues to grow at the same rate, what will the population be in 2025? So we're going to use our equation, P equals 6,000 E to the, use the actual K. I did change it to percent because we usually report growth and decay rates as percentages. But when you plug it into the equation, it needs to be the decimal. So 0.008342 times the time is going to be, instead of plugging in 2025, just plug in 25 because we made 2,000 here. So we'll have 6,000 times E to the, this number times 25. And so we get 7,391.37. So normally you would round that to the nearest whole number, 7,391, since this is people. I don't know what they do. Like a lot of problems will tell you to round to the nearest whole number. I don't know what they do if you don't round it. Like if you give your answer is 7,391.37. I feel like they should still give you that point, but I don't know for sure what they do. That'd be mean. They don't give you the point. Okay, questions? Okay. All right, so let's look at one more here. And so this is a really just bare bones problem. There's no application here. So rate of change of y is proportional to y. So the rate of change of y is dy dt is proportional to, and it's proportional to y. So we just put a y. So we should hopefully recognize this as the exponential growth situation. When you have when you have a derivative equal to just k times that variable, then you can skip all the way to y equals ce to the, hold on,
No, y equals c e to kt.
it's kt, yeah, it is kt. I was throwing me for a second. Because the y would be moved over to the other side. Right. So if it was proportional to the square of y, or proportional to the product of y and z, or something like that, then you would have to set up the differential equation and solve. But if it's just k times that variable, then you can just skip to this. We know when t equals 0, y equals 2. We want to use that first because we want our t to equal 0. And in fact, this is just our initial condition. So if t equals 0, y is going to equal 2. That c value is just going to be 2. If you need to solve that, you can plug in the 2.
Why is the c value 2?
Because e gets omitted.
Because when you plug in 0 right here, e to the 0 is 1. So it just kind of goes away. So c ends up being 2.
Oh.
And that'll happen every time with these types of problems. And then so we have our other piece of information. T equals 2, y equals 4. So 4 equals 2e to the 2k. We'll divide by 2. 2 equals e to the 2k. Natural log both sides. Natural log of 2 equals 2k. And then divide by 2. So our k is going to be natural log of 2 over 2. You can leave it like that, or you can get a decimal for it.
It's just k.
Yeah. So 0.34657. So our equation is y equals 2e to the 0.34657. T.
Or can you do y equals 2e to the natural log 2 divided by 2?
You can use that. Make sure you still have the t there. And so then, if you want to know when t equals 3, the value of y, we're just going to plug in 3. So 2e to the, this number, times 3. And we are going to get 5.657 as our answer.
That's y equals. There's no
Yes.
limit on the test on y.
Probably not. Unless maybe a L'Hopital shows up. L'Hopital's might show up.
Forget that 5, 657, just natural log of 3 divided by 2 divided by 5. That big exponent next to t.
Uh-huh.
Okay.
Okay, so that's sort of just like a bare bones problem that you may see as well. I had a couple more examples that we don't really have time for the whole thing. So your assignment is from page 383. And you have 1, 2, 3, 4, 5, 6, 7 problems. Several of these are going to be ones like the last two that we did that are exponential growth. So when you recognize that it's exponential growth, you can skip to that y equals ce to the kt, which is going to make it much quicker to do those problems. Because this was the assignment that was supposed to go mostly with that part of it, so it's got more questions about it.
Me?
I do need to give you new late work and bathroom passes.
Let's go, babe.
correct. I can't believe you say that.
That's right, thank you for saying that.
This is why don't we just
Well, the softball thing was already like this time of the year.
Tom's always correct. Canceling variables.
Oh, but yeah, I need to. She had a big on there. She said that she's still playing. She made a speech. Bad right off the school.
I'm bad at writing. Can I stick with this? I'm not very good at writing. Yeah.
Wait, we never listened to that song today. Yeah, we didn't listen to the song. Yeah, about the music.
Does anybody else have a speaker?
It's just like in my car, like I have it in my car. Yeah, 'cause Jim went to like the freaking black market or stuff.
I didn't get any. Or unless Bobby stole them, but I didn't know. No, I can't.
It's quite possible I skipped you, but.
I
mean, they're like so trustworthy that.
Hey, Miss Hyatt, can I have this nickel?
The only reason he wants to deal with that is increasing circulation.
Miss Hyatt, can I have this nickel?
Sure. Yes.
Why can't we do those?